Following on from the previous two videos, we got to a stage where we were trying to minimize the area of this triangle here, and the formula for the area of this triangle is given by this, and then we would differentiate it, and then set dA by dx to be 0, and then find out when the gradient the gradient of this will be 0. And well, in the previous video, it turned out to be x equals 0 or x equals 10. Now, because of our problem is that the domain for our problem is that x has to be greater than 5. So this 0 here is meaningless. So this 10 here makes sense. So we got to a stage where x equals 10. Okay, x equals 10. So when x equals 10, the dA by dx will be 0. So when you get to x equals 10, when x equals 10 here, does this mean that this area here will be its maximum, or will it be the minimum area? You see, when you get to x equals 10, you can't tell if it's the biggest triangle or if it's the smallest triangle. You just can't tell. You see, when you see, you shouldn't just blindly jump into differentiating it. We shouldn't just blindly jump from here straight to here, and then find out when it equals 0. We just blindly started here and then blindly differentiate it, and then set it to be 0 here, and then find out when x equals and then we found out that x equals 10. But when x equals 10, we can't tell if this is the biggest triangle or if it's the smallest triangle. You see, you need a sense of what's going on. So when you get to this stage here, what you in effect have is a versus x here. We can't tell if the graph is doing this or if it's doing this. When we blindly differentiate it, it just gave us when the gradient would be 0. So it just gave us this point or this point here, and then it gave us, well, it would be 0 when x equals 10. But the thing is, we don't know if this triangle here is the biggest area, which is in this case here, or if it's the smallest area, which is in this case here. The thing is, we need a sense of what's going on. We need to know what this graph looks like. You see, when you get to this stage here, you shouldn't just blindly differentiate it. You need a sense of what's going on. So when you get to this stage here, we need to investigate dA by dx. Sometimes we would use this to get a sense of what's going on, or sometimes we would use this to get a sense of what's going on. But in this case, use this to have a sense of what's going on. So we know x equals 10. We know something happens at x equals 10 here, but we can't tell if it's our best scenario where this is the minimum, where this is the smallest area, or if it's the biggest area. We just can't tell. We know something happens at x equals 10. You see, to tell, we need a sense of what's going on. So let's use this to have a sense, to have a sense of what's going on. So hang on, let me think. So looking at this formula here, you can imagine this as being, so you've got one block, add another block here. Well, this block here, you can imagine it as being y equals x, because it's a linear. So your graph for this block here would look something like this. Okay, now let's look at this graph. Let's look at this block here. What is this block here what does this block here look like when x gets very, very big? So this is a trick that we normally use here. We've got this thing. Visualize this as one number. Visualize this as one number. So we are trying to investigate what this will look like when x gets very, very big. Okay, so when x gets very, very big, this thing, well, use this trick here. Divide top and bottom here by x. So this is one number here, and then so hang on. So visualize this as being one number. So and then visualize this as being another number. So divide top and bottom here by x. Okay. Remember, we are trying to investigate what this looks like when x gets very, very big. So so you have 15x over x divided by just visualize this as two separate numbers now. So it would be 2x over x minus 10 over x. Now, so this thing here, you can visualize it as this thing here. So you see, when x gets very, very big, this would be 15. Oh, hang on. This would be, this here would be 15 over this thing here would be 2. And then when x is very, very big, you're going to have minus 0 here. So when x gets very, very big, this thing here will have a limit of 15 over 2. Okay. The point is that when x gets very, very big, just this bit here it will head towards some sort of limit. Now look what happens when x is near 5. Okay, when it's dead on 5, this whole thing here breaks down. But let's look at it. Just when it's dead on 5, the whole thing breaks down. But let's just look at it just to the right. So 5.000001. Okay, so let's look at the point of 5.0001. Put it into here. Then this thing here times 2. That would be 10 point, I don't know, blah blah blah, something like this. Take away 10, so this number here will be a positive number, a positive very, very small, a positive very, very, very small. So you have a definite number here over something very, very small. So this whole thing here would be very, very large. I'm not explaining this very well, so you have to bear with me. So when it's near 5.0001 here, this whole thing here would be very, very big. So hang on, looking at this here only, when 5 is here, so just to the right of 5, it would be very, very big. And when x is very, 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 very big, it will head towards the limit of what was it, 15 over 7. So this thing here will look something like this, okay? And then this thing here will be something like a linear line, it will be linear with a gradient of 3 over 2, okay? With a gradient of 3 over 2, maybe something like this, okay? So when you combine these two, it will look something like this. So when you combine the two, your graph will look something like this, okay? So by using this argument here, when you get to this stage here, you can build up a mental picture of what's going on. This is your A, this is your X here. So your graph, when you plot a graph of A when you plot a graph of A equals this thing here, it will look like a U shape. Now because this is a U shape, we know that what we just found out when X equals 10, this here would be a minimum as opposed to a maximum. A maximum would give you, well, when you have a graph like this, then when a gradient is 0, it will give you a maximum. But because we looked at this here and we've established that the graph looks something like this, then we know that this must be a minimum. So what we found when x equals 10 here is a good thing for us. It is actually a minimum as opposed to being a maximum. Okay. So the key part is to have a sense of what's going on. Don't just blindly, when you get to this stage here, don't just blindly differentiate it, because you can't tell if it's going to give us a biggest area or if it's going to give us a small area. We'll have a sense of what's going on. Sometimes you would use this to have a sense of what's going on. Sometimes you would use this. In this case, we use this. Okay, so we built up a graph looking something like this. Then we know what we discovered was that it must be a minimum. Okay, so overall, to answer the question, remember, if you set up theta here, you can express theta to well, in this case here, the minimum would be when x equals 10. Okay, because we varied this length here. We could vary this. We could vary the angle as well. There are lots of different ways of doing this. But when you make x equals 10 here, then this will give us the minimum area. Okay.